The separation of eugenol from cloves by using steam distillation. So before we start getting into what is steam distillation and how you use it to separate eugenol from cloves and what are all the chemical and physical processes happening in there, let's just start off with some easy concepts. What is eugenol? Well, eugenol is a chemical found in high concentrations in cloves and in more minute concentrations in other aromatic spices such as cinnamon and nutmeg. Now, it's supposed to have the properties of it being antimicrobial and antioxidants, an analgesic used as a topical anesthetic, and anti-inflammatory. Now, it's never been clinically proven whether any of these properties are actually attributable to eugenol, but there are findings that do support this. So, as I mentioned before, you can separate eugenol from cloves by using steam distillation. But what is distillation itself? Put very simply, distillation is the process by which chemicals in a mixture can be separated from each other by boiling that mixture at different temperatures. Now, there's many different kinds of or forms of distillation. You have steam distillation, simple fractional distillation, as well as some more niche types. We're only going to be focusing on these two, simple and fractional and steam, with the main focus being on steam. Now, simple and fractional distillation is very simple in how it works. It works by boiling a mixture directly to produce pure vapors yielding a pure distillate. And this is the sort of distillation that you're going to be boiling at different temperatures to yield those pure distillates. Steam distillation, on the other hand, works by boiling a mixture in water, or you can pass steam through a mixture. That works too. But the end result is that the chemicals that you boil out of your mixture will also have water in them, and so you'll be obtaining an aqueous distillate. Now, what we're looking at here is the apparatus for steam distillation, and we're going to go over everything here. So at the bottom, I guess I should show it. At the bottom here is our heating mantle, and this is what's going to be actually heating up our flask that contains our mixture and basically our heat source. Our round bottom flask is what's going to be containing our mixture, our cloves, and the water. It's what's going to be directly heated, and it's where the vapor is initially going to be produced from, and then it's going to go up into our Kleisen adapter. Now we have our separatory funnel up here that has water. That's just for adding more water that gets depleted from the ongoing boiling. But we also have this offshoot output here from the Kleisen adapter. And the offshoot here leads up into our distillation head. This is where a vapor is going to collect, and eventually it'll go down into this condenser here. See, these tubes pump in water and then out water through this tube. And what this does is it creates a large surface area with which is a lot colder, and once this very hot vapor interacts with this cold surface area, it lowers the temperature of that vapor by a large degree. And when that happens, a phase transition occurs in which the gaseous vapor goes back into a liquid, forming our distillate. Our distillate then travels down into this receiver adapter, which is just useful for collecting distillates and making it very controlled to collect the distillate. It collects it in drops and then drops it very nicely down, and it leads into our collection flask. We have our thermoprobe here. That's just for measuring the temperature to see what we're at, and that's how this apparatus for steam distillation works. Now, simple and fractional distillation are a bit different. You're not going to have a Kleisen adapter here, and you're not going to have a separatory funnel filled with water. You're going to replace your Kleisen adapter with a very long piece of glassware known as a fractionating column. On the top of this fractionating column, you would connect your distillation head, your condenser, and your receiver adapter, just as is shown here. the reason you need a fractionating column in simple and fractional distillation is that during simple and fractional distillation, when you're boiling your mixture, all of the chemicals in your mixture are going to essentially vaporize. But the point of simple distillation is that you want to purify your distillate as you're vaporizing it and as you're condensing it. And the only way to do that is to have some of the chemicals that vaporize recondense and fall back into your mixture. And you do this by adding the fractionating column. With steam distillation, though, it's not useful for purifying anything. It's just useful for separating stuff, like separating chemicals from physical components or other liquid components, but not for purification. So we don't need a fractionating column here. We need the Claisen adapter because we need to continuously add water to our flask just to make sure that this experiment doesn't ever run dry. Now, I know, very simple, but when we add water to our grounded cloves, what happens is that, take this line here as just the physical barrier that is the cloves or the dead cells of the cloves, what have you. On the outside is our water, and on the inside of our cloves, extracellular matrix, the dead cells, again, whatever, is our high concentration of eugenol. And over the course of time, some of the eugenol that's in the high concentrations in the cloves will move out of the cloves and into this aqueous layer here, and some of the water will move from the large aqueous layer into the cloves. And so initially, that's how we get eugenol out from the cloves themselves, but then we need to separate it further. Now that we have our eugenol in our aqueous medium, it's time to separate our water and our eugenol from the cloves. But how does this separation occur? Well, to begin with, we need to look at the molecular structures of eugenol and water. When we look at them, we see that water is a highly polar molecule, and in comparison, eugenol is much less polar. This effectively means that the intermolecular bonds between the two is going to be very weak, and generally the two won't mix well with each other. They are immiscible, and although they don't really mix with each other, they can form or they don't mix well with each other. They can form a mixture known as a colloid, and in our specific experiment, this colloid is an emulsion. Now, due to the very weak intermolecular forces between eugenol and water, it doesn't take nearly as much energy to break those forces when converting them to a vapor. And so the boiling point of this colloidal mixture is much lower than the boiling point of pure water, and definitely much lower than the boiling point of pure eugenol. And so when we boil this mixture, it doesn't take nearly as much energy, and when we boil it, we're getting both vapors of water and our eugenol. They reach the distillation head, they go through the condenser and recondense, and then we get our distillate that is from water vapor and eugenol vapor. And so that effectively makes our distillate an emulsion as well, consisting of both water and eugenol. Now, remember how I said that steam distillation wasn't a purifying process? And that's because if it was, when we were to undergo steam distillation and collect our distillate, it would only be pure eugenol. But that's not what we get. We get a colloidal mixture of eugenol and water. And this poses a problem because we can't just boil away our water, because if we try to boil away our water and boil our distillate, we also boil away our eugenol. So we need to find a way to get eugenol out of water. We can do this by way of an extraction. Now, many organic solvents have a very low boiling point, especially when compared to water. And with eugenol being very immiscible in water, it will be very miscible in an organic solvent. So we put our distillate in a separatory funnel and perform an extraction with some organic solvent. In this experiment, we used methylene chloride, but anything that has a much lower boiling point than water will be effective. And swirl the funnel and do what you need to do. And then drain your organic layer from the aqueous layer and collect it in a collection flask. Now, you may think, oh, okay, now we have our eugenol and our organic solvent, get rid of our organic solvent. But before we do that, we have to understand that there is equilibrium at play, especially when swirling the separatory funnel, and that there's bound to be some water molecules left in our organic solvent. And that can pose a problem later on down the line, not only when it comes to purification of our eugenol and analyzing it, but when it comes to boiling it as well. Now, the way to get rid of this water is to add a drying agent. A salt, any salt will do. This experiment, we used sodium sulfate to dry out the water, but you add a salt to it, it should, due to the salt being highly polar, but also not being able to be dissolved by the organics solvent, should form strong intermolecular bonds with the water, effectively drawing it out of the organic solvent. And once we add the drying agent, we then filter our organic solvent or organic solution through a pipette filtration system, which is just a short stem pipette fit with a cotton plug. Run that through the pipette a few times, collect it in another collection flask, and then we finally have our organic solution that should have our solvent as well as our solute or eugenol. And now that we have this, we have our organic solvent that can be boiled at a very low temperature. Now we can actually boil away our organic solution to get pure eugenol. So we set up a hot water bath. I'll put it on a hot plate, heat up the water, and then we put our collection flask directly in the center of our hot water bath. Wait a few minutes, let all of the organic solvent evaporate, and then you should be left with pure eugenol. In the experiment that was performed, 6.0136 grams of cloves were initially used, and at the end of the process, 0.1756 grams of eugenol was obtained. This would lead to a percent recovery of 2.92%. A bit on the lower end, should be around 5%, but also not that bad. The picture in the bottom left is the IR obtained from the pure eugenol. Has all the peaks labeled with the molecule and the relative peak numbers. Don't have time to get into it. On the right is the predicted HNMR of the molecule with the signals and peaks labeled according to the hydrogens on the molecule. And it should roughly look like that. It's probably not perfect, but it doesn't need to be. It's just a prediction. And this was essentially how you separate eugenol from cloves by using steam distillation.